Good morning students. Today we'll discuss about Schrodinger time independent wave equation or Schrodinger wave equation. So last classes we have seen according to de Broglie particle exhibits wave nature. Which particle exhibits wave nature? Moving particle exhibits wave nature. So here moving particle exhibits wave nature. So if moving particle is behaving like a wave, it should have wave equation. So if the moving particle is behaving like a wave, it should have wave equation. This wave equation is developed by Schrodinger. So Schrodinger developed wave equation for the moving particles. So he has developed two equations. Schrodinger has developed two equations. One is time dependent wave equation and time independent wave equation. But in the syllabus we are having time independent wave equation. We'll derive that equation. So before going to this derivation, we should know what is the wave equation in classical mechanics. In classical mechanics, we have studied already wave equation in intermediate. So wave equation is written as y is equal to a sine kx minus omega t, or otherwise it is written as y is equal to a cos omega t minus kx, or otherwise kx minus omega t. So in this, what is a? A is amplitude. A is amplitude. What is omega? What is omega? Angular frequency. And what is K? Wave number. So this is the classical case to represent wave equation. Now quantum mechanically how to represent wave equation, that we'll study now. Next, what is the Schrodinger time independent wave equation? We'll derive now. Okay. Now see here. Consider a particle of mass m moving with velocity v is associated with a group of waves. So in a wave, I am considering a particle. Means particle is behaving like a wave. Now, how to represent one-dimensional wave equation? One-dimensional wave equation in quantum mechanics. So in quantum mechanics, one-dimensional wave equation. One-dimensional wave equation means I can take either x-axis, y-axis, or z-axis. Means I can take x component, y component, or z component. So in one dimension, wave equation can be written as psi. Psi is equal to, see here, this is psi, p silent. So psi, like this we need to write. So psi is equal to a e power I kx minus omega t. This is equation number 1. So in quantum mechanics, we write wave equation as psi is equal to a e power I kx minus omega t. So here, where psi, what is psi? Psi is a function of position and time. Means psi depends on position x and time t. Here it is one dimension. So that's why I am taking only x component. So psi is a function of x comma t, position and time. This is called as wave function. This is called as wave function. Now here omega. Omega represents angular frequency. Omega represents angular frequency. K represents wave number. K represents wave number. This is given as 2 pi by lambda. Wave number is given as 2 pi by lambda. Omega is angular frequency. We can write in terms of linear frequency 2 pi mu. So quantum mechanically we have taken wave equation. We have defined what are the parameters. Psi is called as wave function. Omega is called as angular frequency, K is called as wave number. Okay, now what is A? A is called as amplitude. A is called as amplitude. Now, what we'll do is, we'll differentiate. So, differentiating equation 1. So, we'll differentiate equation 1 with respect to x. So, differentiating equation 1 with respect to x twice. 2 times we'll differentiate with respect to x partially. We'll do partial differentiation. So, we'll differentiate equation 1. What is equation 1? Psi is equal to psi, psi is equal to a e power I kx minus omega t. So, this equation will differentiate with respect to x 2 times. So, if I differentiate first time, I'll get dou psi by dou x is equal to a. What is the differentiation of e power I kx minus omega t? So, e power I kx minus omega t. See here, what is the differentiation of I kx? So, it is e power I kx into ik. So, like that only, a e power I kx minus omega t into ik. So, this is the differentiation for one time. Next, here differentiating twice, 2 times we need to do. So, second time if I do, dou square psi by dou x square is equal to a e power I kx minus omega t, again differentiating ik into ik. So, what I will get? Dou square psi by dou x square, which is equal to I into iota into iota. So, I square is minus 1. So, minus k square a e power I kx minus omega t. So, implies dou square psi by dou x square, which is equal to minus k square. What is a e power I kx minus omega t? So, a e power I kx minus omega t is nothing but psi from equation 1. So, I can write it as psi. This is from equation 1. Okay. Now, so see here, if I take this minus k square this side, so what I will get? Dou square psi by dou x square plus k square psi is equal to 0. K square psi is equal to 0. This is equation number 3. Now, what is equation number 2? What is equation number 2? Wave number, which is equal to 2 pi by lambda. So, what I'll do? I'll substitute in place of k 2 pi by lambda. So, substitute 2 in 3. We'll substitute 2 in 3. We'll get dou square psi by dou x square, dou square psi by dou x square plus what is k? 2 pi by lambda. So, pi square, k square will be 4 pi square by lambda square, psi is equal to 0. Dou square psi by dou x square plus 4 pi square by lambda square, psi is equal to 0. This is equation number 4. Now, we know de Broglie's wavelength. We know de Broglie's wavelength, lambda is equal to h by mv. We know de Broglie's wavelength is lambda is equal to h by mv. This is equation number 5. So, in place of this lambda, I will substitute this. So, what shall I write? Substituting 5 in 4. So, if I substitute 5 in 4, we will get it as dou square psi by dou x square plus 4 pi square. divided by lambda square means h square divided by m square v square. Divided by means denominator will be numerator. So 4 pi square m square v square by h square into psi, which is equal to 0. This is equation number 6. So what I have done, I have substituted lambda value. Okay. So now I want to replace this m square v square. Okay. How we'll do, we'll see now. See here. Next. So we know total energy. Total energy. Total energy is given as energy is equal to potential energy plus kinetic energy. So I can write it as energy is equal to potential energy. I will take it as V plus kinetic energy is half mv square. So implies I'll write this equation as half mv square is equal to this V. I want to take this side, E minus V. So this 2 also this side. So mv square is equal to 2 into E minus V. But here I want to replace. Here I want to replace m square v square. But here I got mv square. So what I need to do? Multiply with m on both sides. So multiply with m on both sides. So I'll get m square v square is equal to 2m into e minus v. So this is equation number. So what equation number? This is equation number 6. So this will be equation number 7. This is equation number 7. So what shall I do now? Substitute. What shall we do now? Substituting this 7. Substitute 7 in 6. So if I substitute 7 in 6, I'll get it as, so see here, this is equation number 6. So I'll get it as dou square psi by dou x square plus 4 pi square by h square. Instead of m square v square, we got 2m into e minus v into psi is equal to 0. Okay. So we'll write it as dou square psi by dou x square plus 4 pi square divided by h square into 2m into e minus v into psi, which is equal to 0. Which is equal to 0. So I can write this equation as dou square psi by dou x square plus 8 pi square m e minus v by h square psi is equal to 0. So this is one form of Schrodinger time independent wave equation. Here there is no time term, t is not there. So psi is a function of position and time, but here time is missing. So this is called as Schrodinger time independent wave equation, or we can write it as dou square psi by dou x square plus, so see here I can replace this 4 pi square by h square with h cross. We know h cross is equal to h by 2 pi. So h cross square will be h square by 4 pi square. Here inverse is there. So I can write it as 2m into e minus v by h cross square, e minus v by h cross square, psi is equal to 0. Psi is equal to 0. This is called as Schrodinger time independent wave equation. So this is the expression for one dimensional Schrodinger time independent wave equation. So this is the Schrodinger time independent wave equation. Okay. This is the case for one dimension. So this is the Schrodinger one-dimensional wave equation. Okay, if I extend for 3 dimensions, so what will be the wave equation if I extend for 3 dimensions? So I need to write it as dou square psi by dou x square, because 3 dimensions means all the 3 axes. Dou square psi by dou y square plus dou square psi by dou z square plus 2m into e minus v by 2m into, yeah, 1 second, 2m into e minus v by h cross square psi is equal to 0. So instead of x, we have written all the 3 coordinates. So what I can take, this dou square, this psi I can take common. So I will take common as, so see here, here dou square by dou x square plus dou square by dou y square plus dou square by dou z square. I will take it as psi as common, plus 2m into e minus v by h cross square psi is equal to 0. Okay, so this I can write it as del square psi plus 2m into 2m into e minus v by h cross square psi is equal to 0. So this is the Schrodinger wave equation in 3 dimensions. So this is the 3-dimensional Schrodinger time independent wave equation. Okay, now see here, what is this del square? Del square is called as Laplacian. Del square is called as Laplacian operator. Laplacian operator, which I have taken it as dou square by dou x square plus dou square by dou y square plus dou square by dou z square. So this is about Schrodinger time independent wave equation. Okay. Now, so what we have taken? We have started with wave function. We have differentiated 2 times this wave function. So I got like this. So next what I have done, I have replaced k square with k with 2 pi by lambda. Next, I have replaced lambda with h by mv. Later, I have calculated expression for m square v square and substituted in this equation. So I got Schrodinger wave equation. So this is the one-dimensional Schrodinger wave equation. So later we have extended this to 3 dimensions. Maximum in the examination they will go for one-dimensional wave equation. So we'll end the topic. Thank you. So for notes, you can see the description for this notes topic. You can see the description. We'll be posting the